Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Kyu-Hyun Chae with us today. Hey, Kyu-Hyun.
Hi,
How are you today?
I'm fine.
Good. Where are you at? What's your geolocation?
It's a little bit south of Seoul, South Korea.
Yeah. Oh, very good. Okay. Yeah, so I'm in Phoenix, so we have quite a number of hours between us here. So I think it's early in your morning and it's somewhat evening where I'm at. Is it coming up on spring in South Korea, or we still got a little more winter to go?
It's still winter. It's still cold. Yeah.
Does it snow there?
It snowed recently, but yeah, it's clear now. Yeah.
Okay. Very good. How are things going pandemic-wise in South Korea?
Still, we don't have much freedom.
Okay.
Yeah, but I don't see many sick people in this country. Yeah, the real problem is we don't have freedom. That's the problem.
Oh, well.
Not sick people. We don't have any sick people here.
Got it.
Yeah, do you know what the problem is?
Yeah, okay, I get it. Yeah, yes. Misunderstood that a little bit, but I got it the second time. Okay. Are there any plans for a vaccine? Are they going to start vaccinating, or it's just not needed?
I think the government is importing some vaccine,
Okay.
and they say maybe late February.
Oh, okay.
Yeah, late this month they may start something.
That's great. Good.
But actually there are many different opinions about vaccine in this country. So
Okay.
yeah.
Yes. I'll believe that. There's probably an equal number of spectrum of opinions in the United States as well. So we'll leave that one alone. Very good. So Kyu-Hyun, what do you like to do for research?
I have been working actually several problems. Recently, I have been interested in testing gravity. Yeah, dark matter problem is closely related to the problem of gravity.
Yes.
And I used to just believe in Newton and Einstein and physics, except that we need to maybe incorporate some quantum aspect. But we are not discovering dark matter even today. So I started sort of interested in some non-standard gravity. And then I thought that I might be interested in testing some aspects of gravity. Yeah, so that's what I'm doing. Whether we can test some important aspects of gravity theories.
Are you primarily an observer, a theorist, a little bit of both?
I would say I'm in between, maybe.
Okay.
Yeah, I talk with observers, but I myself do not observe. Yeah, but my research, the essential part of my research is communication with observers. Yeah, but so I take data from observers, but I do modeling the data. Yeah, that's what I'm doing.
Cool.
So I also need to look into various aspects of theories. Yeah, so I'm really in between.
Yeah, good.
At the moment. Yeah.
Good. Double. And that is going to take us to this really lovely APJ article, open access too, so people can get it get it immediately right now. Testing the strong equivalence principle, detection of the external field effect in rotationally supported galaxies. And Kyu-Hyun, take us away.
Yes, the Newton and Einstein theory of gravity satisfies strong equivalence principle. That means all physics, including internal dynamics, internal gravitational dynamics, should not depend on external field when it is in free fall. But some forms of modified gravity actually predict violation of this strong equivalence principle.
Mm-hmm.
Yes, and actually that, so here we are talking about some specific flavor or framework, actually non-relativist framework that was suggested by Einstein and Milgram back in 1984. Yes, and that predicts actually a violation of this strong equivalence principle. That means the internal dynamics may depend on the external field. Mm-hmm. So this is a unique prediction of modified gravity. So this here we used internal dynamics of galaxies, the rotating galaxies, to test this aspect, the external field effect. And what we are saying is that we have a significant detection of this external field effect from 153 rotating galaxies selected from SPARC database. I think probably many astronomers may have heard of this SPARC database because it's been around a few years. Yeah.
Yep. Yeah, you get a fairly significant detection there. Okay. Where should we go?
Yes. So, well, the standard paradigm at the moment is this lambda cold dark matter paradigm, LambdaCDM. Mm-hmm. That is based on Newton-Einstein gravity, and that assumes cold dark matter, and it is popular, and many people actually considers this LambdaCDM as the current paradigm of the universe. But we have not discovered this dark matter yet. And also there are some problems in small scale physics in the scale of galaxies. Mm-hmm. One is this the satellite plane problem. That means the satellite galaxies are well correlated, and that's not predicted by LambdaCDM simulation. And also, we are seeing a very good correlation between distribution of baryons and the observed dynamics. If dark matter is hosting galaxy dark matter halos or hosting galaxies, then actually we are expecting more diversity. But we are seeing some good correlation. Actually, these correlations started to be observed more than 40 years ago by Tully and Fisher. That's called Tully-Fisher relation. And that's the correlation between rotational velocity and the total luminosity of rotating galaxies. And later, Stacy McCobb and others discovered that this correlation is generalized to baryonic, the so-called baryonic Tully-Fisher relation. That means correlation between circular velocity and total baryonic mass. Here, baryonic mass should include not just the visible matter due to stars, but also cold gas or whatever baryonic matter. This correlation was even more generalized by radial acceleration relation. That's the relation between the radial relation. When there is a circular motion, the centrifugal acceleration can be also called the radial acceleration. And the radial acceleration predicted by the distribution of baryons and the observed radial acceleration that's basically given by the circular velocity, the centrifugal acceleration. That has a remarkably good correlation that was emphasized about 4 years ago by McCobb et al. And in a sense, that radial acceleration relation was, in a sense, some aspect of it was already in baryonic Tully-Fisher relation, but they just generalized it. These are some aspects that's hard to explain by this LambdaCDM. And also one can find many articles discussing many details of problems of LambdaCDM. But here we are not going to talk about those, we are not going to review or talk about those things. Here, I really would like to focus on one unique prediction of modified gravity. Okay. That's not shared by the standard theory of gravity. That's external field effect. That means when galaxy, every galaxy is under free fall, under the influence of the environment. So whether the internal dynamics of a galaxy can depend on the environment. When a galaxy is isolated, and if the same galaxy is under free fall, under relatively strong external field, whether the internal dynamics of two galaxies will be the same or different. Yes. It will be very tiny effect, so it may be very difficult to detect individually, but one can imagine there may be some exceptional cases. Also, if one have enough number of galaxies, one may, so individual cases, there may be lots of noises, but we may detect some systematic trend or some statistical detection. Yeah, so that's so I really would like to focus on this aspect. So this is in a sense independent of this dark matter issue. Even if so, in a sense, even if dark matter exists, even if LambdaCDM, maybe some aspects of LambdaCDM are okay, if what we argue here is really correct, then actually we have to rethink about the laws of gravity, because this result is independent of all other things. Yeah, yeah, because we are talking about unique prediction, of a non-standard theory of gravity. Yeah.
Yes. Cool.
Okay.
Very good. So, yep, you took Spark.
Yes, Spark. Spark database. If I talk a little bit about Spark database, it's a collection of rotation curves. Basically, it's Federico Ralli. He basically surveyed good rotation curves over maybe 20 or 30 years, in the span of 20 or 30 years. And then he selected reliable rotation curves from many groups. And so rotation curves are very important in studying these dynamics. And the other crucial part is the distribution of baryons. So in order to do the reliable analysis, we need reliable distribution of baryons. That part is given by spectral photometry, infrared observation. So what these people did is that they selected reliable rotation curves, and then they also used spectral infrared data to derive baryonic distribution reliably, because that's the crucial part. And also they did lots of additional studies to measure the reliable mass-to-Dirac ratios.
Okay.
Yes. So they basically provide rotation curves and also reliable baryonic mass distribution. Yeah, so excellent data set to do study. Yeah.
Cool. Good.
Yeah.
Do you want to talk a little more about the EFE, or should we head?
Yes. Maybe rather than equations, maybe we just go to figure one.
We'll go to figure one.
Yeah.
All right, figure one. I'm going to blow this up for people. And there we go.
So here, red curve is the radial acceleration that I talked about minutes ago. That's the relation between the x-axis is the radial acceleration predicted by the observed distribution of baryons. So if everything is Newtonian, if there is no dark matter, then the y-axis is observed radial acceleration. It has to be one-to-one relation.
Right.
So the diagonal line.
Yep.
Yes, and that's true until about here, 10 to the minus 9. Yeah, so for acceleration greater than 10 to the minus 9 or so, that's true. So here in solar system, we are in that regime. So
Sure.
Basically, we are using Newtonian dynamics, and that's fine, unless, I mean, except for these relativistic corrections in strong fields. But this below this acceleration, actually, we are referring to this characteristic or critical acceleration as 10 to the minus 10 meter per sec squared. Yes, because that's where the deviation start to be significant. So below this acceleration, we see there is a strong deviation between observed relation and predicted acceleration. And so this red curve is actually basic the aspect of Mond, the modified Newtonian dynamics, and the Bekenstein and Milgram's theory is one particular theory of this Mond paradigm. And this red curve is the Mond relation, and that's observed by radial acceleration relation. And what we are showing here is that the Mond predicts if there is external field, then the curve become like a blue dashed curve. So the E here is referring to the strength of external field divided by this characteristic acceleration, 10 to the minus 10. Yeah, so when there is this tiny external field, we are expecting this tiny deviation. That's what Mond predicts. Bekenstein and Milgram's theory predicts. And the equation 6, in the previous page, equation 6 is the, equation 6 is the some one-dimensional form of this prediction due to Bekenstein and Milgram.
Okay.
Yes. So here, this using parameter called E, that's the external field divided by characteristic acceleration.
Yep.
Actually, this nice looking equation gives the prediction. Prediction one can test.
E goes to 1. 0. Okay, I'm with you. I see.
Yeah.
Cool. So the squares, the colored squares, are the 175-ish number of galaxies.
Yes. 153 galaxies. Yes.
Okay. 153. Okay. I'm with you. Yep. Good. So then we have some prior constraints.
Yes. That's from mostly from Spitzer data. Yes.
Okay.
Yeah.
Let's see. And then we come into figure 2.
Mm-hmm.
I'm going to decrease that so we get it all on there. There we go.
Okay, and these rotation curves Many people have seen this even from high school rotation curves. I mean, flat rotation curves that shows rotation curves are rather flat. Here scales are up to 50 or so kiloparsecs.
Yep.
So it's yeah, it extends to very large distances. And the what's predicted by observed mass distribution are given by this blue, yellow, and green colors. Yes, and if we add them if we add them quadratically, then that's what we expect for total baryonic distribution. Yeah, unfortunately, we didn't show this the total baryonic prediction, but it's not difficult to see that that goes under the observed curve. Yes, and here the okay, so that's familiar to all astronomers. Okay, here we are actually showing the tiny external field effect. Here, the left-hand side is the modeling rotation curve with the external field, and the right-hand side is without external field.
Okay.
And the upper two galaxies are under strong external field, and the bottom two galaxies are very isolated. So they are very weak external fields. And if you compare the left-hand side and right-hand side for two galaxies, NGC 5033 and 5055, we call these galaxies, by the way, golden galaxies, because they have good data and they happen to be under relatively strong external fields among 150 galaxies. So if we had, say, 1,000 galaxies, then we would have more better cases. But unfortunately, we have just 150 galaxies. So these two are the golden from 150, and data are very good. Of course, the experts or radio astronomers can talk about how good these data are. Actually, that's one aspect we need to improve. But these data were selected by Federico Ralli back years ago as best data set. And you see with external field effect, there is very good match to the data for both galaxies. Now, if you look at the right-hand side, without external field, well, you might say, well, that looks good because overall it's okay. Yeah, that was before our paper. People didn't care about this tiny difference very much. And also NGC 5055, you see some difference in the outskirts. Yeah, so these are subtle effects. So people may just don't care about very much. But someone who believed in basically dark matter and Newtonian dynamics, I really actually wanted to, in a sense, maybe I hope to rule out or maybe find strong evidence against Mond. Yeah. That may sound strange, but that was actually my motivation
Okay.
of this project. Because, dark matter is not discovered, but there are many people now who work on MOND and modified gravity,
Indeed.
and also some, quantum gravity, even Berlin emergent gravity and things like that. So non-standard theories of gravity are still around. So I really wanted to somehow rule out. So I looked into this problem, and so I started to talk with this Spark team. Yeah, right now I'm sort of loose association, maybe relatively strong association with the Spark team, although I myself is not not a member, maybe not a member of the Spark team.
Yes.
So you see, so we looked into this, and then because these rotation curves are so good, yeah, these are in a sense disputable, how good they are. Yeah, that's why I'm also looking into other data as well, but they are sort of under progress. Yeah, so anyway, these data set were given years ago. It was not constructed for this study.
Yes.
These data set were already given years ago, and then I just as maybe third party actually entered this problem, and yes, and then it's actually, it looks tiny but very significant if one uses some popular statistics like big or reduced chi-square, whatever. If one uses popular statistics, then one can see very significant difference, statistical difference between these two. And now the bottom galaxies, the bottom two galaxies, they are under weak external field. We don't see any difference between the two. Yeah. So these are just the four galaxies, but it's a remarkable coincidence from just a Newtonian point of view. Yeah, this is just one set of argument of this study. Yeah, we have more arguments from statistical point of view later.
Good.
Yeah, so maybe.
Okay, so let's slide down to figure 3.
Okay, actually, this figure was actually my starting point rather than the figure just we discussed. Okay, this blue dot on the top panel, that was actually just a re-representation of what McGough et al. Already presented years ago. They called them radial acceleration relation. You see, these blue points are very good. They follow red curve very well, and the scatter around the red curve seem just normal, just observational scatter. And so Spark team was just satisfied with that. They didn't think their data might have external field effect. Yeah, so I, as a third party who was actually more believed in dark matter, actually looked at this problem, this data, And I used this generalized equation with the external field effect. And I fitted the data, I refitted data with this generalized equation. And I was curious whether this some statistical tool may give some indication whether when a free parameter is introduced, whether that free parameter will go to will follow red curve, or it will go upward or downward.
Yes.
Yeah. Green here green dashed curve. Whether green dashed curve will go upward or downward, or it will agree with the red curve. This is just purely just a fitting problem using a statistical method. Here we are using a Markov chain Monte Carlo based on Bayesian statistics. And what I found here is that the curve the curve seemed to go downward rather than flat or going upward, and that actually agrees with the prediction of external field effect. The figure 1, the very first figure we saw.
Yep.
Yeah, so this figure was the starting point. Why it's like this? So if one just looks at the top figures, it is actually very difficult to see. Yeah.
Right.
Unless you are really science motivated, it is very difficult to see. You may be just satisfied with the top figures, and then you don't question anymore. But yeah, but I wanted to question. Yeah.
Very good.
More than that. Yeah.
There's a residual.
Yeah. That's what here we are showing here. Yeah.
Interesting. Okay. So that was your start. And we have figure 4. We got some distributions of a perpendicular component.
Okay. Here the deviation, perpendicular deviation is shown. The top panels show this perpendicular deviation for the divided by this the acceleration scale. So the left is when acceleration is strong, so deviation is 0. So the top left, when acceleration is strong, acceleration is the strongest.
Okay.
Deviation is 0. So actually that means it's basically scatter around the red curve. So there is nothing there. Okay. Now, if we move to weaker acceleration regime, in the middle panel, we start to see some deviation. Yep. Here, data points are now in the weak acceleration regime. Now the rightmost figure panel, and now this includes these are the very weak data points. Relatively small number of very weak data points. So here the deviation is now even larger. Yeah, this shows at weak acceleration we are seeing deviations. That's in the data. Yeah,
widening, and it's shifting. If the red line is the centroid of the distribution, it's shifting slightly negative.
Yes. Okay. This the red band shows the median,
Yeah.
the central value, and the bandwidth is bootstrap error of the central value.
Yeah.
Yeah.
Okay, I'm with you. Mm-hmm.
And this bottom panels are showing the fitted value of parameter E. So if we use just the data points in the strong acceleration regime, then actually we have no detection. So E, the fitted value of E is consistent with 0. Okay.
Yes.
Now, if we use data points in the weak acceleration regime, middle panel, then now suddenly we start to have a strong indication of a positive value.
Mm-hmm.
Yeah. And also, if we use the rightmost, the weakest acceleration data points, then once again, we have this positive detection. So we suddenly have this positive detection.
Okay.
Yeah, that's significant. Yeah.
Yep, I'm with you. Okay.
Okay, now figure 5.
Okay.
Yeah, figure 5. This shows the about 110 galaxies. 110 galaxies in the middle panel of the just the figure 4.
Okay.
So yeah.
Mm-hmm.
This shows the fitted value of E that from rotation curve. So the histogram on top, the top histogram, that's from by fitting rotation curves.
Yes.
So we fitted parameter E to each rotation curve, and we have 100 values, and that's the histogram. And here the Sheehan band shows the median value and its associated error, bootstrap error.
Okay.
Now the y-axis, the histogram on the right, histogram on the right, that's actually independent detection from the neighboring galaxies. Yeah.
Okay.
So for each spark galaxy, we have galaxy catalog. We have galaxy catalog, and then we have the neighboring galaxies. So one can calculate the external field, the expected external field at the location of each spark galaxy due to neighboring galaxies.
Right. Okay.
Yeah, that was estimated by Harry Desmond, a young smart guy at Oxford. Harry Desmond.
There's a show.
He calculated, so he measured this part, and then that it shows nice this histogram, and if we we see we see agreement by eye, and the rotation curve, the results from rotation curve fit is quite broad, but that's related to all these uncertainties of rotation curves and baryoning mass distributions. Okay. But they statistically they agree. There is a nice agreement between the two. So this can be shown more explicitly in figure 6.
Yep.
Yeah.
Yes, it does.
Yeah, in figure 6, this is the difference between E fitted by rotation curves
Yes.
and the E environment that's independent estimate from neighboring galaxies. And so this difference is centered on 0 as expected.
Yeah.
And yeah, it has some scatter. And so this shows, it shows explicitly that the two independent measurements are agreeing well. Yeah.
Mm-hmm. No.
Yeah.
Okay. Good. Oops. One. Okay. And here are the fitted parameters for the 153 of them.
Yes. These the shows the posterior distributions of parameters, and it compares with the prior input prior values. So if our prior values were correct, then we don't expect shift. We don't expect much shift in the posterior values from prior values. And you see in except for this mass drive ratio bulge, the middle bottom,
Yep.
middle bottom, that's slightly our posterior value is slightly lower than the observer's prior knowledge.
Yes.
So the observer's prior knowledge was 0.7 in the infrared band. The mass ratio was 0.7, but we are finding a little lower than that.
Yes.
Other than this distance, or the mass drive ratio of disk, and this inclination angle, and also the mass of gas, all these are agreeing very well with observers prior knowledge.
Yeah, yeah. A little bit on I, a little bit on gamma bulge. Yep.
Yeah.
Okay. And it will take us to last figure in the main paper, which is figure 8.
Yes. Yes, this is actually I already discussed this figure, and these are just we are studying
sensitivities.
The systematics. So in the left column, we used only galaxies with very accurate distances, and also this it doesn't include a large amount of cold gas. So it's basically so basically cleanest sample, and it once again confirms. So it has only 553 data points, and so this is the cleanest sample, and it agrees with the main result. And now the middle and the right, these columns are considering different systematics. So in the middle, we are considering 3 times thicker gas disk, and in the right panel, we are giving some mass drive ratio radial gradient in the outer region.
Yep.
Yeah, so I think I don't have time to discuss the details of these systematics, because that's what radio astronomers discuss. Yeah.
Twice. Okay. So then we basically come kind of to the conclusions. What do you think are the punchlines here?
Yes, so we are showing some three aspects of the data. The two golden galaxies and the two isolated galaxies show difference. So four individual cases show difference, and also we have this statistical agreement from 150 galaxies. Yeah, so the statistical detection implied by fitting rotation curves agrees with the estimate, independent estimate from the environment. And also this radial acceleration shows a downward deviation. Yeah, so we have three pieces of results. Yeah, these are just the results. Yeah, so these are the results from the data through this Bayesian statistics. Yeah, and we think this the most natural interpretation of these results is that that's what actually this non-standard theory of gravity, the Bekenstein and Milgram's the modified gravity actually predicted. Yeah, that's a non-relativistic theory. Here maybe I can talk a little about these relativistic extensions of Bekenstein and Milgram theory. And this Bekenstein's Tebeth, that was the relativistic theory, relativistic extension of Bekenstein and Milgram theory. But now we know that theory doesn't agree with the gravitational wave detection. And so that Tebeth might not work. So that's not the right ultimate theory, and not close to right ultimate theory. But there are some attempts, and I didn't actually discuss that. So one can find many attempts are going on, actually promising attempts. So what we are saying is that we are not saying that anything successful from, say, gravitational wave experiments and black hole and the solar system, our results don't contradict those results, because those results are about this the domain where actually this the moon is not moon is not about this strong field, acceleration field greater than stronger than critical acceleration. Yeah, so this is about one aspect of gravity weaker than a critical acceleration. So whatever experiments done in the strong external, the acceleration greater than critical acceleration, that don't contradict our results.
Okay.
And what our results mean is that when a gravitating system, so that cannot be done in terrestrial experiments, because nothing is self-gravitating. Molecules don't self-gravitate. So here, so one can only consider this
We build them.
astrophysical objects like galaxies and galaxy clusters. And here, when this self-gravitating system is in different under free fall, under different strong different external fields, our results indicate that there are something is going on. Yeah.
Well, I gotta love that. Something's going on. So where do we go from here? Given your published article, is there efforts underway to increase the number of spark or spark-like galaxies by a factor of 10? You mentioned radio observations to nail down the rotation curves, the uncertainties. So where do we go from here over the next, let's say, 5 years?
Actually, this getting rotation curves requires a huge amount of effort.
Yes.
Yeah, and this the even rotation curve of one individual galaxy is challenging, and lots of data analysis is going on. So we haven't yet discussed, the survey project. Yeah, because this Spark database itself comes from like more than hundreds of astronomers.
Yeah.
Actually, and over the span of maybe 20 or 30 years.
Okay, so
that shows, and so many current these radio interferometers were used. So it shows how difficult it is. And so right now, I'm more focusing on this more realistic modeling, like three-dimensional modeling. The function we used is just the simplest form. That's basically one-dimensional form of the problem. So right now, I'm more focusing on this more realistic modeling, basically three-dimensional modeling. And also for some galaxies, we have additional data available, and those data may need to be reanalyzed. So I'm trying to improve on the existing data.
Cool.
Yeah.
Well, if I'm not misreading this paper, I suspect that there will be lots of activity to follow up on it over the next 5 years, I think. So it'll be very interesting. Kyu-Hyun, I want to thank you so much for spending some time and walking me through your very lovely APJ article.
Thank you for this invitation and opportunity to talk about these results.
Awesome. Okay. All right, everyone. Thank you. And we'll see you on the next one. Bye-bye.
Okay.